All right. See?
Do we get slides?
Yeah, they'll come up. All right, speaking about MoveIt task planning, we've got Michael and Robert.
Yeah, hello everybody. My name is Robert Haschke. I'm going to present with Michael what we did during the last year, extending MoveIt with task level planning capabilities. And what's our motivation? So I guess we all agree that MoveIt does a quite good job in planning basic trajectories from A to B. However, typically real-world tasks are comprising several of these basic trajectories. And even worse, these trajectories are typically interrelated heavily. So if you consider this pick and place task here with a handover in between, then the initial grasp of the left hand constrains heavily the feasible grasp of the right hand in the handover phase. And up to now, there's no real framework available to plan such tasks. So Michael actually came up with the basic idea initially, and we fine-tuned that during the last year. So we came up with a framework which allows you to easily define those tasks and then perform the planning in there. And of course, we want to be modular, we want to be easily customizable, so programmers should be able to add new stages, their own planning stages to the framework. My special interest is also to have multiple arms in there and multiple hands, because I'm coming from the domain of bimanual manipulation. And of course, you should be able to weight all your solutions according to customized cost functions in order to steer the search process towards the good solutions. Finally, we actually want to replace the existing MoveIt planning pipeline or manipulation pipeline, which is rather limited. Actually, it can only support basic pick and place tasks, and there's no introspection at all there. If something goes wrong, you have no idea why. I need to emphasize that we explicitly don't want to provide a symbolic tasks planning framework. So we assume explicitly that we already know the structure of our task, and we just provide a framework which easily allows to specify this task structure and then provides planning, much like Descartes actually plans between different Cartesian stages as well, but here we are more general in the sense that we can also support non-Cartesian situations. So that's the basic structure Michael actually came up with. So we can compose our task pipeline from several stages, basic planning stages, which can be easily solved by MoveIt. So basic idea of a stage is that you have a state A and a state B, and you want to plan between them. However, now you can combine these or sequence all these stages in order to come up with a complete plan from the very beginning to the very end of your task pipeline. And typically there are several solutions, and you might recognize the figure now from Descartes, which was just flipped in Levi's talk. In our presentations, it's everything from, everything is vertical instead of horizontal. But essentially, it's the same basic idea. You enumerate all the possible states in these intermediate steps, and then try to find a solution path which connects your beginning to the end. We leverage here MoveIt, so we draw on the existing MoveIt framework. So first of all, our interfaces are actually planning scenes of MoveIt, which completely describe the environment as well as the robot state. And this is augmented then by additional arbitrary properties which can be used to configure your individual stages. For example, you can provide a grasp type, or you can specify which hand to use for grasping and stuff like this. we then quickly extended this basic approach with a single linear pipeline, which is essentially already available in the MoveIt manipulation pipeline, to a more general hierarchical framework, which allows you to compose your task in a very modular fashion. So you already know about the serial container, just a sequence of subtasks. Interesting are maybe the parallel containers, which allow you to specify different alternatives of planning. So you might want to plan using the sampling-based planners with RT and stuff like this, or you might want to use dredge-opt alternatively, or whatever simple Cartesian path planning as a third alternative. And all these solutions may be interesting to consider, and we have different these parallel containers come in different flavors. Sometimes you don't have a specific preference, for example, grasping with the left or right hand. Then you can simply specify two of these subtasks or substages for planning with left or right. And all the solutions these children containers provide go into the final solution set of the parent container. Or sometimes you have, so this is the use case for alternatives, illustrated in the second row there. Another use case is that you might have a preference for grasping with the right hand, and only if this fails and you have exhausted all your solution set, then you might switch back to the left hand. And if this also fails, because your object is too large maybe, then you need to grasp with both hands maybe. So this is the use case for a fallback container where the different children are scheduled one by one. And then finally there's a merger, which allows you to plan individual trajectories independently of each other, for example, reaching the object and opening the gripper, but merging them for execution. So typically planning can be done independently in a lower dimensional space, but execution you want to execute both sub-trajectories in parallel. So there's no means in first opening the gripper and then waiting with the arm and then approaching the object, in most cases at least. Of course, this typically also requires some extra feasibility check because there might be interdependencies between these trajectories, so we do this as well, and if this fails, then we keep with sequential execution. And then finally, there's a wrapper container, which simply allows to filter, to modify solutions of which are generated by children. If it comes to a serial chain of stages, then we can easily distinguish between different semantic types of these stages. So planning doesn't proceed typically from the very beginning to the very end in a linear fashion, but usually we need to, or usually we start in the middle. So for example, if you look at pick and place, you first need to come up with grasp poses at your object, and then you can extend this by a lifting motion or by an approach motion. So if we first have generators, here these pick and place or pick generation, which generate so to say seeds for the planning, and these are then extended to larger sub-solution or to larger partial solutions using so-called propagator stages. And then finally, these are the propagators, and then finally we have some remaining gaps between these partial solutions, which are finally filled using connectors, which are typically transit motions from one situation to another. Having distinguished these stages semantically, we can have a similar distinction also on a syntactic level, so to say, distinguishing their interface types. So generators don't read any input at all, so they just spawn new solutions out of nowhere into both of their interfaces, the start and the end interface. propagators read an input from one side of the interface and try to come up with a solution which is then spawned to the other side of the interface. And here it's important to say that planning not only proceeds in a forward fashion from start to end, but also can proceed in a reverse direction from end to start. For example, if you want to approach an object, you already know your grasp pose, your final pose, but you don't know where to start your linear motion to reach this grasp pose. And there you can simply plan in a reverse direction, and then have a reverse, or how we call it, backward propagator. And then finally, of course, we have connectors which read inputs from both sides of the interface and try to connect these states. However, we have combinatorial explosion here because we essentially should combine every pair of states with each other and try to find a solution. However, there might be some compatibility checks. So if we plan for a specific move group, everything comes from MoveIt here, so we work with move groups as well. So if you plan for a specific subset of joints, then all the other joints of the state pair should coincide or should match. Otherwise, there's no chance to plan from A to B if they already are different in joints which are not considered for planning at all. We then have seen that these generators, which actually don't take any input, are not sufficient. Sometimes we need a generator which takes some input from an external, from a remote stage, which is not directly adjacent to the considered generator. So this is, for example, if you have placing. So if you want to place an object, you need, of course, to know which is the grasping pose you have chosen for grasping initially, because you need to use the very same pose. So we need a shortcut, so to say, from the pick solution to the placed solution in order to realize that. And for this, we have this monitoring generator, which simply allows to realize such shortcut connections.
Okay, now having this framework is all nice and well, but of course if you want to use it, that requires a number of implementation of these actual stages so that you can work with it. So we provided quite a number of them for generators. For example, the most trivial one is like, okay, give me the current planning scene, the current world state that MoveIt maintains, and then we can start working with this. This is like usually the start state if you want to execute your trajectory after planning, which is what we usually want to do. And then we have generators for seeding target poses, so in Cartesian space, so that you can specify, okay, I will have to go here at some point, I will have to grasp an object in this frame, which also can sample poses. Compute IK wrapper, which actually provides then the joint solutions many joint solutions possibly for the same target, because we have redundant systems. Then for propagator stages, there's first this two basic stages that has like move towards a target, or, well, we can plan backwards too. Robert just said that. So also move from a target if you know where you start out with, but your planning already tells you where you have to go. This would be move to, move relative, so move with respect to some frame in the environment. But also, and this goes quite a bit away from the standard Descartes view of things, we can also do semantic changes, because basically we're parsing planning scenes. Planning scenes means we have all the current world state, and we can modify things in our current world state. That includes, for example, which objects do I have currently grasped? I can attach and detach these objects from my gripper so that I can do collision checking for these trajectories that includes the collision object. I can also modify the attached collision matrix if I know this. I can reduce computational load a lot for specific substages. And then for transit motions between these key manipulation stages, we provide a connect. most of these also work in joint space on the one hand for Move2, but also in Cartesian space, so you can choose this before. But of course, this is usually not enough because we want to provide an extensible modular system, and this means, of course, you have to be able to provide your own stages. And at the moment, this is currently C++ based, so you can extend an abstract interface, propagating forward in this case, and the only thing you have to implement is a virtual method called compute forward, which receives the current interface stage, which is mostly a planning scene, computes a trajectory from that, and an end scene to say, okay, this is where my trajectory will end. This is what the world will look like at the end, and you can send this forward. Of course, if you want to provide introspectability here, then you can also provide costs. You can provide comments. You can provide custom markers. You've seen this in the Arvis screencast before. So after that, you plug this together in a task. You create a task. You add your custom stages to it, configure them, run task.plan, and, well, you can just execute the first solution if you like to. One more key thing to point out here is for stages such as Move2 or MoveRel, we provide a planner abstraction. So basically, you can plug in any planner you like there, joint space interpolation, Cartesian interpolation, any MoveIt pipeline that we have, maybe also TreadUp in the future. I hope so. Yeah, and when you actually plug this together for a real quite complex example of manipulation, then this might look something like this. You start out with the current state of your system. You plan to pick up a bottle that is somewhere in your environment, which is generating a grass pose, generating a whole trajectory that picks up, attaches, and lifts your object. You have a second generator that computes the motion going towards towards a glass that is somewhere in the environment. You compute a purring trajectory, and afterwards you place the object back. So you can actually run this on the robot. You get some nice illustration, also especially here for the purring trajectory. You see the purring motion in advance already. You can execute this on the robot. Okay.
So a key feature of this manipulation framework is that you can also inspect if something goes wrong. So you already have seen that we can visualize the final trajectory together with all the markers which the user attached to its solutions. But we can also here in the Arvis plugin navigate all the solutions and look at the failed ones and see what actually goes wrong. So this framework is still a lot of work in progress. So we have several features on our list which we need to still implement. First of all, we want to replace the existing pick-and-place capability, but there's also work going on in providing or extending the existing Arvis GUI so that you can configure your task interactively there and then maybe save and load from YAML or directly generate your C++ or Python code. We have some ideas on execution handling. So currently you take your final solution and pass it over to execution, but there might be options that you can already take a partial solution, an initial partial solution, and already execute it because, for example, it's the only one solution you found for this initial part, or you don't care and simply want to proceed fast forward and pass already this partial solution for execution. And that, of course, then constrains the subset of solutions you should consider for further planning, and so forth and so forth. One important step is, of course, scheduling, which is not yet finally done. We have some priority queues which allow for sorting your solutions according to cost. However, what is not yet done is actually the stage scheduling. And because I'm running out of time, I'm just mentioning that there is a Python wrapper available already, and then that's the final slide for you.
So also, you will hear that again. There's World MoveIt Day in 3 weeks. Please consider participation. Of course, all the issues we have with the task constructor are also up for discussion. If you want to take them for the day, please do so. And the very last thing to point out, the framework by now has been evaluated on quite a variety of robots. So you see some of them here. If you want to see the thing live in action, you might want to have a look at the Mobile Manipulation Hackathon at ROS next week. We present a Tiago-based bartender setup there, which is in the lower right, and you might actually see it working in action, assuming it works. Thank you.
All right, if there's one quick question from the audience. I've got one for you. If someone from the community has created a custom stage, how would be the best way for them to notify you of this or other community members?
So assuming it's relevant for everyone, pull requests, or just open source your custom packages. We have a plugin interface.
Great, thanks a lot.